Okay, let's look at 3 and 4. So what are where's the axis of symmetry and the vertex of this equation? Well, what makes this one different than the first question is now we are in standard form, ax squared plus bx plus c. Okay, when that's the case, we can't grab the vertex explicitly from the equation. There's no h's and no k's there. So what we will use is that formula for the axis symmetry. There it is, right there. And how we read that, I kind of don't like having that negative there. A great way for you guys to think about this is think about that as just being the opposite of b divided by 2a. So let's take a little bit of stock here on what we got here in this equation. So the axis of symmetry, we would have a would be 2, and b, which we would need, it would be positive 8. So the axis of symmetry would be x equals the opposite of b. So if b is 8, I want negative 8 divided by 2 times a, so 2 times 2. So then keep on going here. We have negative 8 divided by 4. And so then x would have to be negative 2. So there's our axis of symmetry. Now how about that vertex? Here's a couple things that we know. And maybe I'll steal a couple of these pictures down here. See that axis of symmetry? I'll draw in a couple more dashed lines. There's a symmetry line right there. And what's true about that axis of symmetry, or even this guy right here, that axis of symmetry has what they have in common with that vertex is they have the same x coordinate, which means that the y coordinate that's paired up with that vertex can be found by simply plugging in that x value that we just found for that axis of symmetry and plugging it into the function. So if we were to do that, excuse me, and let's go ahead and plug in a negative 2 here. Now be very, very careful. Now how you plug that in, many mistakes can happen finding that y for that vertex. So I have a positive 2 times a negative 2 squared plus 8 times negative 2 minus 4. The mistakes that happen is students try to multiply this together first, when really what they should be doing is squaring that negative 2. Negative 2 squared, isn't that a positive 4? And then I'm going to take a positive 4 and multiply by that 2, which should give me an 8. And then it's okay to multiply those two together, so that'd be negative 16. So we're going to add a negative 16, and then we're going to subtract a 4. So then 8 plus a negative 16 would take me down to negative 8, and then a negative 8 minus a 4 should put us at negative 12. So in other words, our vertex of this parabola should be located at the x value of negative 2 and the y value of negative 12. Can you think of any way that we could probably check this answer? Maybe the graphing calculator. A graphing calculator can check this answer. Shoot, the graphing calculator could have even given us this answer to start off with there, and we could have even done that first. Take a look. So now that I've typed in the graphing calculator 2x squared plus 8x minus 4, let's just double check to make sure I typed that in there right. 2x squared plus 8x minus 4. Yep, we got it. Graph it. Okay, great. There it is. What are we looking for again? The axis of symmetry and the vertex. So let's go to the table of values. Prediction, where's that vertex located? Probably some negative value for x. So let's kind of go and find it. And looking at those y's, and I see another little pattern going on right there. Take a look. Negative 12, negative 2, negative 12. See those two negative 10s above and below it? That's a good sign. That tells us that we've reached the minimum value right there, which in turn makes that the vertex. Not only is that the vertex, but that's also our axis of symmetry of that negative 2. So that answer that we just got right here of the axis of symmetry being negative 2 and the vertex being negative 2, negative 12 is perfectly legit. Okay, let's look at number 4. State the maximum or minimum of the graph. Well, if a parabola opens upwards, then doesn't that mean that we have a minimum value? And that minimum value is that vertex that's right there. So this one shouldn't be too bad. We have a minimum value of, and by the way, once you find that vertex, which should here be at negative 2 comma negative 1, whenever we're talking about a value, we're always talking about the y value here. So we have a minimum of negative 1, okay? And then when we state the range, when you look at all the other subsequent y values, they all have something in common. Aren't all of those y values greater than or equal to -1? So I can state that that range is the set of all numbers where y needs to be greater than or equal to -1. There's that. Okay, let's look at B over here. Our vertex is up here, which means that we must have a maximum here. And what's that maximum? It's still the y value. Where's the vertex here? I think that's at 3, 4. So that y value, we have a maximum of 4. And then the range, what should be true about all these y values? These y values are all less than or equal to 4. Okay? So hopefully we now have a good grip on what's going on there. Just read those very carefully in case those are multiple choice. Short answer, it's not that big of a deal, right? Especially when you got a graph here in front of us. Okay, let's continue. Let's graph some quadratic functions, or quadratic equations. Plot 5 points, you guys know all about that. Let me look over here at B. When B is in vertex form like this, remember, vertex form, these are awesome. We have 1, and then we have our H and our K, so our vertex on this guy needs to be at opposite, so -1, and then -2. So 1 to the left and 2 down, there's our vertex right there. Okay, you've heard me talk many, many times about how the fact that if A is 1, that parent function, its width is exactly the same. All that happened here was a translation of 1 unit to the left and 2 units down from the original parent function. So from the vertex, isn't it true that 1 squared is 1? And then with parabolas we get 2 for 1. Let's reset back to the vertex. If I were to travel 2 squares to the right, 2 squares being squared gives me a total vertical change of 4 units. So I'm going up 4. Notice I'm not looking at the y coordinates, I'm counting those squares. Okay, so there's those. And then very elegantly and very, very precisely, I have a great looking parabola there, right? Looks perfect. Okay, what about when it's in standard form? What options do we have here? Well, I guess we could still go and get the axis of symmetry, just like we did before, and that would be that whole x equals -b, the opposite of b, divided by 2a. And if we started there, in this case, the opposite of b would be a +4. And then, ooh, careful, a is -1, so 2 times -1. So really, I have 4 divided by a -2. So my axis of symmetry should be 4 divided by -2, so that should be -2. X equals -2. So here's what I would know. My axis of symmetry right over here at -2. There it is. What I don't know is where the vertex is. So, same sitch. Let's plug in that -2 and find that vertex. So, y would be equal to, ooh, careful, -2 squared, -4 times -2, plus 2. Now don't treat those two negatives as a positive first, square it first, get the +4, and now we have a -4 minus, ooh, wait, -4 times a -2, that actually would be +8 plus 2. Uh-oh, I hope this thing fits. -4 plus 8, that puts me at 4. And then add the 2, that puts us at 6. Shoo, that was close. Okay, because now if I look at this x compared with this y, I now have a vertex that's situated right here at -2 and +6, which would put us right there. Now, look at that a value. See how it's -1? It's the parent function. See this guy over here? The one that we graphed over here on the right, where it was 1 and then up 1 and then 2 and then up 4. Because it's a -1, we can go 1 and then down 1 from that vertex. Reset. Go 2 squares to the right. I can go 4 squares down. Make sure I count that properly. 1, 2, 3, 4. There we go. 2 for 1. There's that guy right there. Boom. Parabola.